Okay, welcome to part 2 of complex numbers, and we will start by describing the Argand diagram, which is also known as the complex plane, where we take an axis where we have the x-axis is now the real axis, and the y-axis is the imaginary axis, and we have an origin. Now, if we have a complex number with real value, with real component A and imaginary component B, that lives here, Z is A plus B times J, then this is how we display it in a diagram like this. On the y-axis we have the imaginary parts, so 1, 2, 3, 1, 2, 3. And so this is the point where this is the point where 1 is visualized, and this is the point where I is visualized, or 2I, or 3I. And we can draw complex numbers in this diagram. Now, this point here would have, if we see it as a vector, it would have coordinates a, b, and the concept of seeing this as a vector will be used later. Now we can extend this diagram to all 4 quadrants. So if we have -2, -3, -4, and here as well, -1, -2, -3, this will be Z is equal to 3 minus 2J. This will be -3 minus 3J. We have 3 plus 2J here. And this is a way to put all these complex numbers in a diagram. Now, returning to the idea of a complex number as a vector. If we take our diagram where we have the imaginary axis and the real axis, which I'll abbreviate with im and ri, and we have our coordinates A and B, and of course we have an origin, and this is our complex number Z is plus B times J. Now, if we represent this as a vector, starting at the origin, then recalling some parts of engineering, mathematics and modeling, we know that a vector has a certain set of properties. It has a length, or otherwise called modulus. So we can determine the modulus of a complex number Z. We typically denote that by Z with 2 vertical stripes, and we call that thing R, and that is basically the length of this vector. A length of a vector with coordinates A, B, we know by Pythagoras' theorem, is A squared plus B squared. So now we know what the modulus is of a complex number. So what can we do with this? Well, recall that if we had 2 vectors, v1 and v2, and we wanted to know the distance between these 2 vectors, we will take the modulus of the difference. And if we want to take the distance between 2 complex numbers, we can now do the same thing. And so this would represent the distance between, let's say, these 2 complex numbers if we calculated the modulus of its difference. Now, besides having a modulus, a vector also had an argument, theta, which was the angle with respect to the positive horizontal axis, which is not the positive x-axis now, but is our positive real axis. And it doesn't really matter if we take this from 0 to 2 pi, but typically we take what's called the principal angle, which means that we take theta in the interval minus pi to pi with plus pi included for well, this is typically what is taken. We will see, however, that we will deviate from this and that won't matter. But this, in any case, is the principal value of theta. And of course, if we have an angle of 3 over 2 times pi, it is the same as minus pi over 2. So this angle here, minus pi over 2, is the same angle as 3 pi over 2. Well, how do we find this? We know that if we draw the triangle with height b, a, and theta, we know that the tangent of theta is b over a, which means that theta is the arctangent of b over a, or sometimes written as the inverse of tangent, the tangent like this. Both are, of course, the same. So this is how we can determine the argument. So now we have a complex number. Z is equal to a plus b times j, with modulus r is equal to the length of z. We have argument theta, and this allows us to write our complex number in a different way. This way is the Cartesian way, where we have coordinates on the x and y, well, our real and imaginary axis, and we have another way where we can write coordinates which can be in the polar form, where we use this modulus and this argument. So we can write z in polar form, where we say, well, it has a length and angle theta. This is purely notation, but it's going to prove to be a very handy notation, because if, and I'll show you an example of a complex number of this form. So z equal to 1 plus j. So if we draw that on a very small diagram, that is here, 1 plus j. And we know it has an angle of pi over 4, and it has a length of the equal to the square root of 2. So we can also write z is equal to the square root of 2 with an angle of pi over 4. Why is this form convenient? Well, if we use this form, multiplication and division become practically trivial. Before we get there, I want to introduce another form to write our complex numbers in, which is simply taking this diagram and which I will draw again, and again looking at the properties of this vector. So we have z is a plus b times j, and we have a modulus r and an angle theta. But this is a triangle we know more about, because we know this distance a is equal to r times the cosine of theta, because we know that a divided by r is the cosine of theta. This is just rewriting it. We also know that this distance b is equal to r times the sine of theta. So not only can we write z as a plus b times j, if we use these expressions for a and b, we see that z is equal to r cosine theta plus j times r sine theta. Or we can take r and write between parentheses cosine theta plus j times sine of theta. This is another form, so we now have three forms for a complex number. We have z is equal to a plus b times j. We have z is equal to r with the angle theta, so this is the polar form. And we have z is equal to r cosine theta plus j times sine of theta. And these three forms each have their benefit when performing certain calculations. Now, returning to these representations. Just let me get rid of this. If we redraw our diagram, and we have A and B, so this is our imaginary axis, our real axis, and our origin, we can show where z is, so z equaling A plus B times J. Now we know that its complex conjugate is equal to z minus B times J. And here, this is equal to z. The complex conjugate of z is A minus B times J. But if we now look at all the other representations, if this is theta, this is minus theta. So its complex conjugate is equal to r with the angle minus theta. Now, because we know that the cosine of minus theta is the cosine of theta, and the sine of minus theta is equal to the to minus sine of theta, we also know that the complex conjugate of z can be written as r times cosine theta minus j times the sine of theta. So if we know what the modulus and arguments are for a complex number, we also immediately know what the modulus and arguments are for its complex conjugate. So the book details the steps for multiplication, which use some identities, some geometric identities. Now, it would be confusing if I tried to do the whole thing here, but if we take z1 is equal to r1 with the angle theta 1, and z2 is r2 with an angle theta 2, using those identities, we can also rewrite this as r1 cosine theta 1 plus j times sine of theta 1 is equal to r2 cosine of theta 2 plus j times the cosine of theta 2. If we were to multiply these with each other, then we would get z1 times z2 is equal to r1 r2 times cosine of theta 1 plus theta 2 plus j times sine of theta 1 plus theta 2. And we see that when we multiply two complex numbers with each other, we multiply the moduli with each other and we add the angles. So this will be r1 r2 with angle theta 1 plus theta 2. And the details of this are in the book. Now, if we look at division, z1 divided by z2, there's also an explanation in the book of this. But what I wanted to show you is that we don't need an overly complicated calculation for this. If we look at 1 over z2, then we will write this as, to write this as another complex number, we would write 1 over z2 times its complex conjugate divided by its complex conjugate. Now, we know that a complex number times its complex conjugate was its real part squared plus its imaginary part squared. This was a2 plus b2 squared. Yes. Well, we also know that that r2 is the square root of a2 plus b2 squared, which means if we take a complex number and multiply it by its complex conjugate, we get its modulus squared. So, taking that, we know that this is z2 complex conjugate divided by r2 squared. Now, z2, the complex conjugate, is r2 with the angle of minus theta 2. And we divide that by r2 squared, which is equal to 1 over r2 with angle minus theta 2. And this was equal to 1 over z2. So if we want to take 1 over a complex number, or the inverse of a complex number, what we end up with is a complex number with modulus 1 over the modulus of the original number, and as an angle minus its original angle. So now, using that, if we have z1 divided by z2, which is z1 times 1 over z2, we can write this as r1 with angle theta 1 times 1 over r2 times angle with angle minus theta 2. And we already knew how to multiply these numbers, because we would multiply the two moduli and we would add the two angles, and for dividing two complex numbers we get the division of the moduli and the difference of the two angles. Now, I probably brushed over this rather quickly. I will do that again very quickly. If we have z is a plus b times j, then we know that z times its complex conjugate is a plus bj. A minus b times j is equal to a squared plus a times b times j minus a times b times j minus b squared times j squared. These two cancel out, and j squared is minus 1, so this is equal to a squared plus b squared. Now, if we want to calculate the modulus here, this length using Pythagoras is equal to the square root of a squared plus b squared. So if we were to square this expression, we would get the modulus squared. So we use that z times its modulus, its complex conjugate is equal to the modulus squared. And so when I take 1 over z and multiply it by this fraction, the numerator becomes z2 times its complex conjugate is its modulus squared. And this is why, using the polar form to multiply or divide complex numbers is a lot easier than writing them out in Cartesian form. Alright, so this concludes the end of part 2, where we introduced the Argand diagram, the polar form of a complex number where you could write it in terms of a cosine and a sine term, and we showed that dividing and multiplying in the polar form is a bit easier. And in the next video we will continue with different forms of complex numbers and a couple of theorems attached to them.